everyone! So it's been a while since I've posted an integral on this channel, which is why today I decided to post an integral on this channel. And the integral we are going to do today is the integral from 0 to infinity of the natural log of x over 1 plus x squared with respect to x. But before we do that, I would like to mention that next week will be the geometry week on my channel, which means next week from Monday up until Friday, I will post one geometry problem every day. And with that announcement out of the way, we can finally start solving this integral right here. And to get started solving this integral, I would like to use integration by parts. So we need something to differentiate and something to integrate. And we are going to differentiate the natural log of x to get 1 over x, and we're going to integrate 1 over 1 plus x squared to get the inverse tangent of x. And now we can simply adjust our integration by parts formula to get that this is the natural log of x times the inverse tangent of x evaluated at 0 and infinity minus the integral from 0 to infinity of, and then we'll have 1 over x times inverse tangent of x, which is just inverse tangent of x over x dx. Good. And now, let's see. If we plug in infinity into here, we get natural log of infinity, which is infinity, times inverse tangent of infinity, which is pi over 2. So it seems that at infinity, this whole thing is infinity, therefore the whole thing diverges, right? Well, not so fast, because here we have an improper integral of type 1, which is over an infinite integral. Therefore, this is technically the limit as some t goes to infinity of the integral from 0 to t of, well, our integrand. So we can write that into our expression, so we will get that this is equal to the limit as t approaches infinity. Let me rewrite that infinity here because it was not the best infinity I had ever written. So this will be t and this will be t. And now let's see. If we plug in t here, we get natural log of t times inverse tangent of t. So this will give us the limit as t goes to infinity of natural log of t times inverse tangent of t. And then we have to subtract this thing evaluated at 0. But if we plug in 0 into here, we get natural log of 0, which is negative infinity, times inverse tangent of 0, which is equal to 0. But infinity times 0 is an indeterminate form, which means we'll have to use limits to evaluate this expression. So let me do that in red, just so it's in a different color. Like this. Okay, so the limit as t goes to infinity, as x goes to 0 of the natural log of x times the inverse tangent of x. And now, let's see, as I said earlier, this is a 0 times infinity situation, which is an indeterminate form, which means, well, we'll have to rewrite our limit a tiny little bit more into the limit as x goes to 0 of the inverse tangent of x over 1 over ln x. And now, if you plug in 0 into here, you get 0. If you plug in 0 into here, you get 1 over negative infinity, which is itself 0. And now we have a 0 over 0 situation, which means we can use L'Hopital's rule. So we will get the limit as x approaches 0 of, differentiate the top, you will get 1 over 1 plus x squared. Differentiate the bottom, don't forget to use the chain rule, you will get negative 1 over x ln squared x. And now we will factor out that negative sign because it's a constant. So we'll have the limit as x goes to 0 of, and then 1 over x ln squared x is just x ln squared x in itself. So we will get x ln squared of x over 1 plus x squared. And now what happens if we plug in x is equal to 0 again? We'll get 0 here, negative infinity square, which is infinity here, and on the bottom we'll get 1. So the numerator is an indeterminate form, which is, well, 0 times infinity, and the bottom is something we can evaluate using direct substitution. So we can split our limit into two limits, namely the limit as x goes to 0 of x ln squared x times, my eraser was about to fall like it always does, the limit as x goes to 0 of 1 over 1 plus x squared. But then, as I said earlier, plug in x equals to 0 here, you get 1, which means this whole thing will vanish and we'll only be left with this limit. And as I said earlier, this limit is an infinity times 0 situation, which means we will have to rewrite our limit. So we will get minus the limit as x goes to 0 of natural log squared of x over 1 over x. And now plug in 0 into here, you get infinity. Plug in 0 into here, you get 1 over 0, which goes towards infinity or negative infinity. But since it's technically a 0 plus, it will go to positive infinity. But either way, we have an infinity over infinity situation, in which case we can use L'Hopital's rule again. So we will get negative the limit as x goes to 0 of 2 times ln x, and don't forget to use the chain rule, you will get 1 over x all over negative 1 over x squared. And now the minus signs will cancel out, the 2 can be factored out, and 1 over x squared is just x squared in itself, which will cancel out with the x to leave only x. So we will be left with the limit as x goes to 0 of x ln x. And now, again, this is a 0 times negative infinity situation, which means we'll have to rewrite our limit again in a similar way as we did before. So we will be left with the limit as x goes to 0 of natural log of x and not ln of x over 1 over x. And now we can, again, use L'Hopital's rule. So we will get the limit as x goes to 0 of 1 over x over negative 1 over x squared. But then we can factor out the negative sign to get minus 2 times this limit. And then 1 over x squared is x squared. X squared over x is equal to x. And the limit as x goes to 0 of x is just 0. And 0 times anything is equal to 0. Therefore, this whole thing is equal to 0. Which means this 0 term vanishes, which means we don't have to subtract anything. And what we really need to subtract is our integral, namely the integral from 0 to t of the inverse tangent of x all over x with respect to x. And now, our next step will be to evaluate this integral, but not completely, such that we can substitute it back into our limit and get some nice results. But before I do that, I would like to clean up the board. Okay, so now that I've cleaned up the board, we can start evaluating this integral right here. So, to do that, I would like to introduce a substitution, namely, we will let x be equal to the tangent of some theta. And why do I do this substitution? Well, it's because plugging x into here, we'll get inverse tangent of tangent theta, which is simply theta in itself. Okay, so now our dx will be secant squared theta d theta. And then here our theta will be the inverse tangent of x, applying the inverse tangent on both sides. And now we will plug both of our bounds into our substitution. So we will be left with the inverse tangent of 0 is 0 and inverse tangent of t is inverse tangent of t. So we will be left with, as I said earlier, theta over x, which is the tangent of theta, times secant squared theta d theta. And now I would like to simplify this secant square of theta times over tangent of theta a tiny little bit. So, secant squared theta over tangent theta. So, secant squared is simply 1 over cosine squared theta, and 1 over tangent theta is cotangent theta, which is cosine theta over sine theta. This cosine theta will cancel out with 1 of the cosine theta in the bottom, so we will get 1 over cosine theta times sine theta. But then if we multiply both the numerator and the denominator by 2, we will get 2 over, and then the bottom is exactly the double angle identity for the cosine, namely sine of 2 theta, and we can rewrite this a little bit as 2 times the cosecant, not the cosine, the cosecant of 2 theta. So now we can plug this in to our integral. So we will get the integral from 0 to the inverse tangent of t of 2 theta times the cosecant of 2 theta d theta. And now I would like to introduce a substitution, namely u will be equal to 2 theta, which means du will be 2 d theta, which means d theta will be du over 2. And now let's see. That 1/2 right here will be factored out since it's a constant, and we'll be left with plugging both of our values into our substitution. We'll get 0 and 2 inverse tangent of t, and here we'll get 2 theta, which is u, times the cosecant of 2 theta, which is u, and don't forget the du. And now I would like to use integration by parts on this integral. So we'll have something to differentiate and something to integrate. And we'll differentiate u because, well, differentiating it's easy, it's just 1. And we'll integrate cosecant u. But now, what is the integral of cosecant u? Okay, so to evaluate the integral of cosecant u, we will use Weierstrass substitution. So the integral of cosecant u du will be, so to use Weierstrass substitution, we will let some t be equal to the tangent of u over 2. So this will have the effect of making that du will be 2 over 1 plus t squared dt, and sine of u will be 2t over 1 plus t squared. But then taking the reciprocal on both sides, we get that the cosecant of u will be 1 plus t squared over 2t. So now that we have everything, we can just plug everything into our integral. So we will get cosecant u, which is 1 plus t squared over 2t times 2 over 1 plus t squared dt. And now the 1 plus t squared will cancel out, as with the 2's, and we'll be left with the integral of 1 over t dt, which is just the natural log of the absolute value of t plus some arbitrary constant. But then our interval is strictly positive, which means for all, say, x lying in that interval, x is strictly greater than 0, well, greater than or equal to 0, which means we can drop the absolute value bars. But what is t? Well, t is just the tangent of u over 2, so this will be the natural log of the tangent of u over 2 plus some arbitrary constant c. Or, no, minus some arbitrary constant c. This is better. So, we'll have the natural log of the tangent of u over 2 right here. And now we can just use our usual integration by parts formula. So to get 1/2 times, and then we'll have u natural log of tangent u over 2 evaluated at 0 and 2 inverse tangent of t minus the integral from 0 to 2 inverse tangent of t of natural log of tangent of u over 2. The integral from 0 to 2 inverse tangent of t of ln of tangent of u over 2 du. Don't forget to end the bracket. And now, let's see. If we plug in 2 inverse tangent of t, we will get 2 times the inverse tangent of t times, and if you plug this in here, you will get 2 inverse tangent of t over 2 is inverse tangent of t. Tangent of that is t, so we will get 2 inverse tangent of t times ln t, and multiplying it with the 1/2 will give us will simply give us inverse tangent of t times ln t, and then if we plug in 0, so if we plug in 0 into here, we will get 0, but if we plug in 0 into here, we will get 0 over 2, which is 0, tangent of 0 is 0, and natural log of 0 is negative infinity. Therefore, we have a 0 times infinity situation, and do you know what that means? We'll have to use limits again. So we will clear this part of the board such that we have a little bit more space. And here we go. So the limit as u approaches 0 of u natural log of the tangent of u over 2. And now, as I said, this is an infinity times 0 situation, which means we can rewrite our limit a tiny little bit more as the limit as u approaches 0 of u times, the natural log of the tangent of u over 2 over 1 over u. And now, plugging u into here, you will get negative infinity. Plugging u into here, you will get 1 over 0, which goes to infinity or negative infinity, depending on which way you're approaching. But either way, we have an infinity over infinity situation, which means we can use L'Hopital's rule without angering the gods of mathematics. So we will get the limit as u approaches 0, and then differentiate this. Don't forget to use the chain rule. You will get the cotangent of u over 2 times the secant squared of u over 2 times 1/2 all over negative 1 over u squared. And now the 1/2 and the negative sign can be factored out since they're both constants. So negative 1/2 times the limit as u approaches 0 of u squared times, and then this should be similar. This should be familiar to you. This is exactly the same expression that we simplified earlier when we were simplifying secant square over tangent theta, but instead of theta we have u over 2. So this will just be 2 times the cosecant of 2 times u over 2, which is u. But then the 2's will cancel out, and cosecant u is simply 1 over the sine of u. So we can rewrite our limit as the limit of, as u approaches 0, of u squared over the sine of u, like this. But then, plug in 0 into here, you get 0 squared, which is 0, over sine of 0, which is 0. So now we have a 0 over 0 situation, which means we'll have to use L'Hopital's rule again. So we'll have the limit as u approaches 0 of 2u over the cosine of u. But then plug in 0 to here. In the bottom we'll have 1, which is good, and in the top we'll have a 0. So we will be left with simply 0. Therefore, this whole thing just goes to 0, which means we won't have to care about subtracting that. And we have to subtract this integral, and don't forget the 1/2 because it's distributed to all the terms. So minus 1/2 times the integral from 0 to 2 inverse tangent of t of the natural log of the tangent of u over 2 du. But then we will stop evaluating this integral here because we will plug this into our limit. And here's why we will do that. So we'll have, instead of that integral, we'll have distribute the minus, we'll get minus, let me just open my pencil, minus the inverse tangent of t times the natural log of t, and not the ln of t for the millionth time, I guess. And then minus minus is plus, so plus 1/2 times the integral from 0 to 2 arctan t of natural log of the tangent of u over 2. Don't forget the d. And now these two terms are exactly the same, which means these two will cancel out. And then plug in infinity into here. As t goes to infinity, the inverse tangent of t goes to pi over 2. 2 times pi over 2 is pi. So we will only be left with 1/2 times the integral from 0 to pi of the natural log of the tangent of u over 2 du. So this is good because now we have reduced this integral into this limit into this integral. And now I will clean up this board and we can continue, or should I say finish, evaluating this integral. Okay, so now that I've cleaned up the board, we can finally finish evaluating this integral. And to begin, I would like to introduce a substitution. Namely, we will let some t be equal to u over 2, which means dt will be 1/2 du. But 1/2 du is exactly what we have here. Therefore, our integral will be the integral from, plug in 0 into here you get 0, pi into here you get pi over 2 of the natural log of the tangent of t dt. And now, to solve this integral, we can make use of a property called the king property. And what the king property states is that if you have an integral from a to b of f of x dx, well, this is exactly the integral from a to b of f of a plus b minus x dx, like this. And now we can use this property onto our integral, but don't worry, I'll leave some links down there in the description as to why that identity holds. And well, as I said, we can use this property on our integral right here. So we will get the integral from 0 to pi over 2 of the natural log of the tangent of 0 plus pi over 2 is pi over 2, so pi over 2 minus t dt. But then, let's do some mental maths. Tangent of pi over 2 minus t is cotangent of t, which is 1 over the tangent of t. But then 1 over the tangent of t is just tangent of t to the negative 1. But since it is inside the logarithm, we can bring the negative 1 out of the logarithm and out of the integral since it is a constant. So we will be left with minus the integral from 0 to pi over 2 of the natural log of the tangent of t dt. And now we'll say that this integral is equal to I, which means that now we'll add that integral to itself. So we'll get 2I is equal to. But then these two integrals right here are both equal to I, which means we can add them up. So we'll get the integral from 0 to pi over 2 of the natural log of the tangent of t dt, and then minus the integral from 0 to pi over 2 of the natural log of the tangent of t dt. But then these two integrals are exactly the same, which means they will cancel out to 0, which means 2I is equal to 0, which means because dividing both sides by 2, provided of course that 2 is not equal to 0, we get that I is equal to 0. And this is our answer, but let me rewrite it more nicely. This means that the integral from 0 to infinity, let me rewrite that infinity because it wasn't the nicest infinity, of the natural log of x over 1 plus x squared with respect to x is equal to 0. Whew. That was a nice integral, one could say. Well, it was a nice integral. And as always, this is your video. We're watching the video. I'll see you in the next video. Bye.